Welcome everybody. This is our Module 5 of the Graduate Statistics course, University of Cincinnati. As I mentioned in the introductory video, today I'm going to try and introduce you to statistical inference, to the logic of it. Try to explain to you and help you understand why statistical inference is needed, why all of these tests, so that you leave this course minimally knowing why you're doing things like t-tests and ANOVAs and regression analysis. Why? Not just I can't implement it, but why those things are needed and what is the logic behind that's common and kind of underlies all of those tests. So this is video lecture 1. Let's go. So we'll start with an example of a study on gender discrimination. And the question that has driven that study is the following. Does the indicated gender of an applicant affect promotion decisions? And down here, you have the reference of the study whose data we're going to discuss. So first, the method. 48 male bank supervisors were given the same personnel file. So everything in the file was identical for all of the 48 male bank supervisors. And they were asked to judge whether the person should be promoted. With one caveat. Half these bankers received the file with the applicant assigned sex marked as female. And 25 of these 48 bankers were randomly selected to receive the file of the applicant whose assigned sex was marked as male. Now, the overall, let me get myself out of the way. The overall data indicates that 35 out of 48 of the bankers decided to promote the applicant. However, because of the question we're asking about gender bias in those promotion decisions, we need to know what's the gender breakdown of those promotions. So let's look at the data next. So the first thing we do with data, we describe, we summarize. How should we summarize this data? Remember, the response variable is the promotion decisions, and it is a categorical variable with 2 levels, promoted, not promoted. So different from the kinds of variables that we worked on during our descriptive statistics labs, where we obtained mean and median and we did plots and stuff. Here, all we have are counts, right? How many were promoted and how many were not promoted. So this is the overall count. But as I said, we need some breakdown of these totals based on whether the assigned sex of the shown in the file was male or female. So this is a contingency table because we're looking at promotion contingent on the gender that showed up in the file that they were making the decision about. So now let's look at the data carefully here. Here are the number of managers that received the file marked as male who decided for promotion, 21. And this is the number of managers who decided for, let's not promote this person yet. And those are the numbers for the female. And remember, we had the same number of managers receiving a file marked as male as the number of managers receiving a file marked as female. So it's a fair comparison to look at the raw data. So we had 21 out of 24 who decided to promote the applicant when the applicant was marked as male. And we had 14 managers deciding to promote, remember, the same applicant because everything was the same in the file, except that the file was marked as female. So there is a difference here of 7. 7, of course, makes sense in the context of this particular data set, but it's always nice to put numbers in context. Because what if the totals here were different? A difference in 7 may or may not be meaningful. So it's always nice to look at the data in context. And in this case, it means to compute the percentage of applicants marked as male that were promoted, and the percentage of applicants marked as female that were promoted, right? So if you do it this way, it doesn't matter if there are differences in the number of managers that received male and female files. All right, so let's look at that. So here's our contingency table. We want to compute the proportion of males that were promoted out of the total, the proportion of managers that decided to promote the candidate when they received the file marked as male. So that would be 21 out of 24, 21 divided by 24, which equals about 88% of the sample. So 88% of the managers whose file was marked male said to go ahead and promote. Now let's see the percentage of managers that decided for promotion when the file was marked female. That was only 14 out of 24, which is 58%. So in summary, one more time with feelings, 88% of the managers in this sample said to go ahead and promote the applicant whose file was marked as male. 58% of the managers who received the file for the same applicant, except it was marked as female, said to go ahead and promote. So we're talking, in summary, think about it, we're summarizing the data. In summary, we have a 30% difference in promotion decisions, just based on gender, because every one of the 48 bankers received the exact same file with the same qualifications. All right, so that's the summary statistic that we're dealing with. Now, I mentioned in our introduction to the module that identifying a particular summary metric is a beginning, right? So at least we know now we're describing and we know we're dealing with a 30% difference in promotion decisions in our sample. Our sample had 48 bank managers. And that's suppose we want really to make an inference about promotion decisions of managers, of all managers, not just this 48, but all managers, right? So we found a difference of 30%. So the question we must be asking in order to be critical about that data is the following. Is a difference of 30% in decisions likely or unlikely, assuming that there is no gender discrimination? That is, assuming the null hypothesis. Would it be common to see that difference if I keep sampling managers, right? So imagine I do another study and I sample 50 managers now, and I look at the difference in decisions. And then I get another sample and I look at differences in decision. How frequently would it be for me to see a difference of 30% if there is no gender discrimination? Imagine in the real world, no gender discrimination. And I keep sampling managers, right? I'll probably not see 0% difference because, you know, the world is messy and there is variability. I don't expect to see the exact same decision rates. But if there is no gender discrimination, how likely would it be for me to see a difference that is as large as 30%? And that's what inferential statistics tells us. It tells us that likelihood to see, well, even if nothing is going on, you know, just by chance, it's pretty common to see a 30% difference. Then we have to decide that there is no gender discrimination, and this is just normal variability that happened in that is expressed in our sample, right? That the real difference is 0%, But, you know, it just happens that in this sample, the difference turned out to be 30, but that's pretty frequent event to happen under random conditions, under conditions where there is no gender discrimination, right? But if we find out that, no, the probability is kind of low to find that difference of 30% under conditions that are purely random, right? When there is random binary decisions, it's hard to see a difference of 30%. Then we decide that we need to kind of dismiss, at least we don't provide evidence for the null hypothesis that there is no gender bias in favor of a hypothesis that gender bias might be a thing, right? So that's what inferential statistics does. And what we'll do now is introduce you to that process via what we call simulation. And you'll know what that means when we get to the lab, all right? So I'll see you there, and this is it for lecture. Now we're going to do hands-on activity to figure out whether we should take a 30% difference as something to trust, or if it's likely due to chance. All right? See you there. Bye-bye.